So this is one. So now it's my pleasure to introduce you to Doug Higinbotham, and he is the associate. What's your title?
This week, title is Acting Associate Director of Experimental Nuclear Physics. Next week, he'll be Acting Division Director of CEBAF Experimental Physics.
Why he getting demoted? So
And I'll explain why in my talk.
okay, he has been a friend of this summer school for many years, and he will entertain you now on what we do with all the beam that we know very well. So, Doug, please.
Yeah, thank you. All right, and I lost the clicker. There we go. All right, so since our last speaker, Ryan, discussed 1980s cars, I thought I'd start with that because my son, who's far closer to your age than you are to mine, decided to buy a 1989 Porsche 944, which for the entire senior year at Virginia Tech has been sitting up on blocks. He does have it now rolling allegedly, and it will be coming home where he will continue onward with his project car. You can get the car that doesn't actually work for about $5 grand. He has dreams because if you go online and look up a 1989 Porsche 944 that actually works, it looks pretty, $30,000, $40,000. So he has dreams. All right, to the talk. All right, so I do have some overlap with Ryan's. So I've asked him to stay so he can correct me or at least make fun of an experimental nuclear physicist perceptions about our accelerator. I'm going to do a little bit of history. I'm going to talk about the National Lab system. I'm going to talk about wild things like M&O contracts, FFRDCs, all kinds of acronyms. It's kind of relevant right now because Jefferson Lab is just ending a contract transition. The company that Ryan and I work for is ending on Friday, effectively. And on Monday, there is a new company running this laboratory. So we are transitioning from Jefferson Science Associates. If you look outside on the sign, it's JSA. I don't know whether they're going to pull that off over the weekend or what, but it's going to be Suratech. And I'm going to talk about, a little bit about why, what's going on, what does that even mean? All right, let's get started. I'm going to span nearly a century, and if I want to trace back, where did this national lab system, the Department of Energy, Jefferson Lab, where did it come from? If I want to make a single line all the way back in time, I can blame Einstein. 1939, he's writing a letter to the President of the United States. In 39, Einstein's already extremely well known, well respected, and he's writing a letter to the president warning him that the Germans, the Nazis, are on a path to be able to deliver a weapon of unimaginable destructive power, an extremely powerful bomb. With hindsight, we all know what that is. At the time, it's like, okay, we all know Einstein's genius. What's he talking about? Is this something to be taken seriously? So Einstein sees it early. Eventually, the president, the administration sees it. This is something real. There is a race which the United States hadn't even started in. The Germans are well in advance. 1942, the United States Army Corps of Engineers establishes the Manhattan Engineering District. It becomes known as the Manhattan Project. This is a number of locations being used, a lot of them in the middle of nowhere. Los Alamos, Oak Ridge, Hanford. What do these places have? Mostly in the middle of nowhere. Cheap power, and in some cases, easy access to to water. Not true for all of them. So Los Alamos, we know from making the bomb, Oak Ridge National Lab, a lot of work on creation of isotopes, separation, and the one that's a royal mess today is Hanford. Hanford's a super fun site. Hanford is where we made the plutonium, where the second bomb dropped on the Japanese. So one was enriched uranium, the other plutonium. The process to make a little bit of plutonium and uranium is actually easy. I'd say any nation could do that. You can go to the site at Hanford and stand next to the facility where they did that today. It's not activated, it's not hot. To separate plutonium from uranium, that's chemistry, right? I have two different isotopes. In the distance, you can see the location where that was done. Some of the nastiest chemistry humans ever came up with. You went from elephant-sized amounts of uranium with a little bit of plutonium to come up with a little mouse-sized plutonium. Anyway, 1939, letter from Einstein. If Einstein got the ball rolling, you could argue that Oppenheimer is the father of the National Lab system. And we're not going to hold it against him, but he's even a theorist, like Alberto. Amazing man. I don't think theorists are usually noted for being, let's say, the charismatic leader. He very much was, and there are other examples as well. Working hand in hand with the United States military on this project. You're bringing in a professor, he's bringing in a lot of academics. So people not unlike yourself, but now back to the 40s, to work on creating a new weapon. You might imagine that scientists don't necessarily want to be part of the military. And Oppenheimer made an absolutely critical decision, and it carries through to this day. So you can imagine you have a project, General Groves, he made the Pentagon, he's in charge of the Manhattan Project, working with Oppenheimer. They want to give everybody military rank, so that scientists would have a rank. That's how we do things in the military. Oppenheimer resisted, and in the end, it was left to him to make a decision whether this should become something with rank or a different structure, more civilian-oriented structure where the scientists are one removed from the federal government. If you've seen the movie, you know that all wasn't smooth with Oppenheimer, especially into the 50s. He lost his security clearance, certainly had a lot of, let's say, misgivings about having created a weapon of such destruction. His family carries on his legacy, looking at peaceful uses of nuclear power, nuclear energy, and worrying about non-proliferation. But the decision that he made to not have the scientists become part of the federal government is what I'll say really is the father of this system, this strange management and operation system that the national labs of the Department of Energy are built on. It could have been very different with one decision. So going forward, so after the end of World War II, most are seeing this as, so uranium, plutonium, these are amazing new weapon systems. And that is what at first was all people were thinking about. But it did change. So as I go from the 40s into the 50s in the Atomic Energy Act, people are starting to realize, no, this actually can have peaceful applications, power, other uses we use today. So we have 4 nuclear reactors in the state of Virginia. Most of the power that's lighting up this room right now is from nuclear energy. So there are certainly peaceful uses as well as destructive. in fact, destructive. You go down to the Newport News shipyard. You can see the Nimitz aircraft carrier, or sorry, the Enterprise is being taken apart. They're getting ready for, I think it's a new one they're building. Anyway, every one of those carriers has a couple nuclear reactors. We also put the nuclear reactors in the subs. So even within Newport News, a lot with nuclear energy. Going forward in time, so again, from the Manhattan Project, Atomic Energy Commission, spinning off the Nuclear Regulatory Agency, very brief time, this Energy and Research and Development Administration. This did not last long. 1977 is the Department of Energy, and I'm assuming there are only 3 of us in the room who were born then? Yeah, okay. All right. No, I'm older than the US Department of Energy. All right. So over the years, what has coalesced is a system of national labs. A lot of it started from that weapons production that started during World War II, continued on through the Cold War. As of today, there are 17 national labs. Some of them are located in multiple locations. That original Los Alamos National Lab in the desert, Oak Ridge National Lab, Tennessee. You'll notice there is no Hanford. Hanford's now a cleanup site, national park. It's actually quite beautiful. South of it is Pacific Northwest National Lab. That's kind of the legacy of the part of the Manhattan Project. You'll notice that on this map, different colors. Most of the blues are weapons labs. It might not surprise you that much of the funding for the Department of Energy still revolves around nuclear weapons. That's mostly Sandia National Labs, Livermore, Los Alamos. But there's many more, and then there are labs not even shown on this plot that aren't part of this DOE National Lab System. They're responsible for the weapons systems. But of course, that's not all DOE does. A lot with energy. National Energy Technology Lab, located in West Virginia and Pennsylvania. National Renewable Energy Lab. Does anyone in the room know what that's called today? They had to change their name.
About the Rockies, right?
Yeah, National Lab of the Rockies. Renewable Energy Labs are out right now. So National Lab of the Rockies, very recently changed their name. Idaho National Lab, small nuclear reactors, both for peaceful purposes, but also submarines as indicated. Ames, a very small lab. They make Jefferson Lab look big, very much into chemistry. And then you have your basic energy labs like Jefferson Lab, Fermi Lab, Brookhaven. I'll talk a little more on each of those. This is a way to visualize. So I've got all these national labs doing all kinds of things. This is a visualization of all the different missions that the labs are doing, from basic science, Fermi Lab, Jefferson Lab, Fermi Lab, high energy physics, Jefferson Lab, nuclear physics. We're very much basic science, fundamental research, basic properties of matter, and single program. So this is something Jefferson Lab wants to get away from. But as of right now, Jefferson Lab is nearly completely funded by Department of Energy, Office of Nuclear Physics. Fermi Lab is similar, funded by high energy physics. At some of the bigger labs like Brookhaven, they get multiple streams. So Brookhaven with light source, basic energy science. They're building the EIC, nuclear physics, many things. Some of these laboratories are really into everything, like Berkeley, Argonne. SLAC is shown transitioning. They were a single purpose lab for a long time, becoming multi-purpose. And as you go from this basic science side, you start to get into the technology side. So the big 3 weapons laboratories, Lawrence Livermore, Los Alamos, Sandia. So they're doing a lot for the National Nuclear Security Administration. We really, as far as that aspect of DOE, we don't interact. There's also that energy part of DOE with National Energy Technology Lab, Idaho National Lab, and National Lab of the Rockies. And then some oddballs. Savannah River National Lab. So Savannah River was only very recently made a national lab. They were part of the complex making materials during the Cold War. So Savannah River site, very much part of that weapons program. And they've spun off Savannah River National Lab. They're doing a lot with cleanup right now. So all this work with plutonium, pretty much anywhere they made plutonium is now a cleanup site. And it shall be being cleaned for decades to come. It's really unbelievable mess. That's in the United States. If you look at Russia, they're not even cleaning it up. So eventually, hopefully people will get to that. And at the very top, Pacific Northwest is one of the, well, they're all interesting labs. It's interesting in that it is considered an Office of Science lab, but most of their money comes from the National Nuclear Security Administration. This gives them a very interesting place because unlike these three, which are weapons labs, it isn't. And it allows them a bit of freedom that the other labs don't have. That gives them a competitive advantage. And as far as their grades, and yes, the national labs get grades, they're graded like a science lab, but most of what they do is classified. And you like, well, teacher, I can't show you my homework, it's classified. All right. All right, so 16 of these 17 labs, you're at one of them, are FFRDCs, federally funded research and development centers. There are a lot of special rules that come with being an FFRDC. We're strange entities. Jefferson Lab directly receives money from the federal government, but we don't bid for it. So if you think of, I don't know, Newport News Shipbuilding down here, I mentioned making carriers, they bid for that. They are a company. They are making a product for the federal government, and they deliver that product to the government. These federally funded research and development centers directly receiving money from the government to do an aspect of research. Often things that the private sector doesn't want to do, he doesn't care about. And there's a whole long list of what constitutes a federally funded research and development center. The thing I put in bold, FFRDCs cannot compete with the private sector. So one of the questions that comes up at Jefferson Lab a lot, why don't we make our own liquid nitrogen? If you've been watching these large trucks several times a day come to site with liquid nitrogen, we use a lot of it. Could we build a plant and liquefy nitrogen ourselves? Yeah. There's a local vendor that can supply the nitrogen. We cannot compete with the private sector. We shall buy our nitrogen from the private sector. That's an example of where we don't compete. Private sector doesn't care about quarks and gluons, at least not directly. I care a lot. I imagine you all are interested in that aspect of fundamental basic research. We're not competing with industry. Other places where the national labs don't compete with industry are things that maybe industry should do, but aren't going to do. Grid stability, for example. So Idaho National Lab of the Rockies, they put a lot of time and energy into protecting the energy grid in the United States, stability of the grid. How do you recover from a power outage? How do you manage a modern grid with so many different types of energy sources? If you're a company and you're making solar panels, you really care? Are you going to spend your money researching how to stabilize the grid? Probably not. It's something that the national labs do and the federal government funds. It is needed. We want the power to come back on after a power outage. And if you interested at all, my talk's posted on the site. You can click here. You can look at all the FFRDCs in the United States of America. Yeah.
So is this like a legal requirement that you can't compete with the private sector? Because it just seems like logically you would just make your own like.
I didn't mean to. Sorry. Yes, it's actually a legal requirement. It's what defines an FFRDC. That's part of the requirement. It's that whole list. And part of it's the reason that you can't compete with the private sector is you have special access to the government. So you have a conflict of interest if you.
Makes sense. It just seems extreme.
It is maybe a little extreme, but I'll give you another example. So at Los Alamos National Lab, they do isotope production, which they actually sell. So they'll do full cost recovery of isotope production. I'll call it sort of. So it's full cost recovery on the process that you asked for. If you start thinking about the entire infrastructure of this facility they have, you're not paying tiny fractions. It was really just to make your isotope. Medical people, industry love that. They're happy to pay full cost recovery from the isotopes from Los Alamos. No one else wants to do it. It would be a gargantuan investment to make such a facility. So it's picked up by the national labs and we're not competing with anyone. On the other hand, as an entrepreneur, you go, oh, I know a new way to make isotopes. It wouldn't be so expensive. And you jump into that market, they'd literally have to back off in the private sector.
Stop doing it?
They would have to stop doing it. If you could really compete. Now, it's not going to be, we think you compete. It would be, you're really there to fill the need for the nation producing those isotopes for less than the national lab. I guess it wouldn't necessarily have to be less, but it's pretty hard to compete the national lab on something like that, just by economy of scale. They're within Los Alamos.
They don't have to make a profit.
They don't make a profit. And the way they calculate full cost recovery, it makes it very cheap because you're not paying for a lot of things that in real life or as a private company you'd pay for, like the security guards and all that kind of infrastructure, tax on the land. That's not part of that full cost recovery. But you can think about labs in the DOE, but this also goes to medicine, healthcare, lots of places where, if you're worried about, I don't know, outbreak of Ebola, companies may not worry about it, but that is something as a nation you do need to worry about and invest. So you'll also see that a lot of these on this list are with biological. All right, other fun terms, GO-GOs and GO-COs. Government owned, government operated. Jefferson Lab is government owned. This is a government building. You're on federal land. This causes problems. But we are contractor operated. There is only one of the labs in the 17 that is not a GO-CO. It's a GO-GO. Government owned and government operated. And that's NETL, the National Energy Technology Lab. This is one that historically was concerned with coal mining. It was developed when coal miners were dying in explosions and no one could figure out why. It was actually kind of neat. The canaries weren't dying. The mines were exploding all of a sudden. Anyone have a guess why coal mines might explode all of a sudden, but the canary didn't die? Yeah, they're mining coal, so probably something with the coal. But some mines explode, other mines had no problems.
Dry air, you get coal dust.
The dust, it was absolutely the dust. So you could be mining with the exact same process, but depending on what type of coal you were mining, and there are many types of coal, you created a lot more dust. And with a lot of dust in the air, one little spark, you have an explosion. And in hindsight, you go, oh yeah, dust. I have enough of it and I have combustion, great, got explosion. In hindsight, it all makes sense. When it was happening at the time, especially since, the mine just exploded. What the heck happened down there? Anyway, that's why that particular agency was started. It is government owned, government operated, which means the lab director of that lab is a federal employee. The lab director of this lab is an employee of a company, right? Today, Jefferson Science Associates, in a few days, Ceratec. But still, he's an employee of a company. He's not a federal employee. It makes the interaction between the lab directors even a little awkward. If you're a federal employee, you are very restricted on what you're allowed to receive as a gift. So even something as simple as going out to eat with the lab directors, that one is special. So one thing that is fascinating about the GoGo lab is about 2/3 of the people who work there are contractors. So actually the majority of the people are still non-federal employees. But the lab staff, the main members are. So Ryan and I are not federal employees. We are employees of Jefferson Science Associates, soon to be Ceratec. And this in some ways is nice. We are insulated. We are not federal employees. We are not at the mercy of the whim of the current administration. Whereas if you're a federal employee, thou shalt follow the president's directives. That's part of being the federal employee. So we're insulated one step back. And that goes all the way back to Manhattan Project in insulating the scientists from the military. It's one step removed. M&O contracts, so management and operation contracts. This, if you really get excited about bureaucracy and government, you can read the Federal Acquisitions Regulation, the FAR, and all these details. So you ask about GOCOs and GOCOs and FFRDCs. A lot of it ends up going back to the FAR. We are operated underneath a contract. So this is government land. It's a government building, but Jefferson Science Associates has the responsibility for managing it for the government with oversight. So there's a site office upstairs that watches that everything's going okay. And the reason I said earlier it can be a problem, it is a federal research lab. And depending on what's going on in the world, that may mean we don't allow people to come here. And this has been most recently a problem with China. And someone who says politics, but still, if you can't pass the American background check, you can't come on site. A few years ago, it was Russia. Right now, it's China. So that's the unfortunate part of being federal land and following federal rules. Generally, it is not an issue. But you can imagine as things heat up on the world stage, it becomes an issue. All right, so this is a list of the national labs and who their management and operation administrator is. One of them is not applicable, the GoGo, that's just federal government operates that one itself. I know it's a lot of words. The only one I wanted to point out to you is the one I made in bold, which is Battelle. So there is one company that manages a lot, over half of the national labs. It's Battelle. Their home base, their main lab, original lab, Pacific Northwest National Lab. It's a nonprofit organization, and to be blunt, they do an extremely good job running the labs. They have very good understanding what the Department of Energy wants. They appreciate the fact that at DOE labs, you put safety first. Very good processes and procedures in these competitions to manage a lab. Battelle often comes out on top. You'll notice that they're not always by themselves. So if you look at Oak Ridge National Lab, Battelle partners with the University of Tennessee to run that laboratory. And there are other examples. But they don't run them all. They don't run this lab. And some have had the same M&O contractor forever and probably will have the same one forever. So Little Ames at Iowa State University you could walk past that laboratory and never know you were by it because it looks like another academic building on campus. The land is owned by Iowa State. They leased the building to the federal government. So how the heck is another contractor gonna come in and bid on this? So some of them are kind of locked in. On the other hand, the ones that are locked in are relatively small. The big ones have changed, including Los Alamos. So this is a list of most recent changes in contractors. Sandia, one of the biggest labs. Sandia, Los Alamos, both nearly 30,000 employees. So 2017, 2018, Savannah River 2020, and the two most recent, Fermi Lab, that was January 2025. It's mostly still run by the same underlying group. So University of Chicago has been running Fermi Lab forever. But they now have a new consortium, a new limited liability company. So Fermi Forward Discovery Group, which is led by University of Chicago, then has many other groups with it. Jefferson Lab nearly completed its contract process, let's see, a year ago. It all fell apart with the new administration because the contract that Fermilab is actually under has a lot of diversity, equity, inclusion language in the contract. You change administrations, they look at the contract, it had not yet been awarded for Jefferson Lab, and they're like, no way. And we actually redid the entire process, the bids, everyone had come back through, they updated the contract, the call. Anyway, it is now over. The announcement of who won the bid was on March 31st. There were at least 3 serious bids for this lab. The winner was Sura Tech. This still has at its bottom the original contractor for this lab, which was Sura, Southeastern University Research Association. That's the original. They then made this Jefferson Lab Jefferson Science Associates LLC 20 years ago, and a new consortium with the biggest change now is a university partner. They've partnered with Virginia Tech, huge engineering school in the state of Virginia, to make a new partnership. So still Sura, kind of all the way, new partners, both the university partner, and they actually brought in a number of partners to help with safety. Lockenecker and Associates, they've also brought in Honeywell, a lot of help. It is quite a process. It's a big deal to win one of those bids. Yes.
So what is the so like who exactly is like bidding for these like contracts, and like what's like the the motivation for not just like renewing the contract or
Money.
okay.
So it's not a lot.
Yeah.
No, but the contractors for these laboratories, so Battelle, for example, and Saratech will be given a fee for managing the labs. What's interesting about running a lab and the fee, you start off with the maximum and along the way you lose. So if you screw up and you have safety incidents or other problems, you're not delivering, they subtract, subtract, subtract. So you know the maximum amount you could receive for managing the lab. And if you're having issues managing the lab, you'll receive less and less.
Okay.
There are other things that people find interesting in running a lab that includes access to the intellectual property of the lab, the patents. So as the M&O contractor, you are managing the patent portfolio of that laboratory. That can be extremely interesting. What was evident in Jefferson Lab's most recent bid, it was the new data center we're building on site that caused a lot of interest in this round of bidding. And 20 years ago, I don't believe there was any other serious bid. This time there were 3. And I'm just speculating, but I really think it was the addition of new money coming in for a data center at this site sparked a lot of interest in getting their foot in the door at this facility. They have access to that technology. All right. So the United States Department of Energy. That's kind of a transition slide. How would you explain, knowing what you know now, I know that's quite limited, but still, what does the United States Department of Energy do? Oh, come on. Nothing. What do they do?
Nuclear physics research to make energy and bomb.
Not too bad. I like that. All right. So my favorite answer to that question comes from this fine gentleman, Ernie Moniz. He was professor at MIT. He was Secretary of Energy in the Obama administration, and that is his real hair. I've always been quite jealous of the hair. Quite a prominent nuclear physicist, as you may well imagine, anyone who can become a tenured professor at MIT. All right. His answer to the question, what does the United States Department of Energy do? It does quarks, quagmires, weapons, and windmills. Your answer wasn't far off. He just got it down to 4 words. Quarks, quagmires, weapons, and windmills. What the heck? All right. Quarks, Jefferson Lab, Fermi Lab, building blocks of matter. Quagmires, environmental cleanup. This could also be data centers. Weapons, the big one, which you mentioned. And windmills, energy, solar, wind. Okay, what's fun is then I'll take this plot and go, okay, Ernie Moniz came up with these 4 great answers, but show me the money. Yeah, we're not even second. Mostly weapons. And this percentage, this is mostly cleaning up from making the weapons. And this is cleaning up from separating plutonium out of uranium. We have plenty. So don't worry, we're not making the mess anymore. We have plenty of plutonium. We don't need to do that anymore. But the cleanup from that chemical process to separate the plutonium out, this is what we're cleaning up. It's a royal mess. You can thank Ames National Lab for not only figuring out the chemistry of how you would separate plutonium from uranium. That's not necessarily hard. What Ames figured out that was really unique, how to do it at scale, an industrial scale, how to build a canyon in the middle of the desert, and they are called canyons, where you do batch chemical processing, the big chunk of uranium in one side and a little thing of plutonium out the other. Nasty, nasty. This is the barrels that you see pictures of leaking out. That was from, much of it's from that process of separating out the plutonium. At the time, who cared? It's the 1950s, going into the 60s. It was all going to be over soon anyway. Why do I need to worry about cleaning it up? Well, we made it through. It's cleanup time. Basic science research, energy. All right, so that's the big picture, national labs. You are getting to spend your summer, for a few weeks anyway, here at Jefferson Lab, one of the 17 national labs. As of right now, around 85% of our funding comes from nuclear physics. We are in the process of branching out. The biggest branch will be HPDF, this high performance data center. That's bringing in new money from an agency called OSCAR, Advanced Scientific Computing. This will bring in a second big pot of money into Jefferson Lab. And once that facility is online and becomes a user facility, we will have truly made the transition from single purpose to a multi-purpose laboratory. But none of this would be possible without CEBAF. So I go all the way back to the beginning. It was actually quite a competition to have this facility located here. When it became clear that the little state of Virginia has the possibility of getting an accelerator, other places wanted it, including MIT. What was the Bates Accelerator wanted this facility, SLAC, Chicago. There were a lot of ideas. This is what we ended up building. It is not what we said we were going to build. The very first lab director of this facility, Herman Grunder, a bit rough around the edges, but he's one of these visionary people who can navigate political waters to get the bid to build this accelerator and then switch to a different technology. And the technology he switched to was superconducting RF. In the original bid, this was going to be another normal conducting accelerator. If they had built a normal conducting accelerator with the beam loading and everything else, there was no way this machine was even going to work. I challenged Ryan to tell me how we were going to run with a normal conducting accelerator, the multiple bunches with different beam currents, where you have to take into account beam loading.
We do that off the top of my head.
So if you read the original bid and you think about it, I think you'll know that Grunder always knew he was switching. Nevertheless, going to superconducting was risky. To win the bid, you do the safe. Once you have the money, back then anyway, you could go to the risky. And Ryan already gave you that basic layout. So starting from a source, we started with a thermionic gun here at the laboratory. Take a wire, bend it, you'll liberate electrons, easy peasy, just run a current through it. Nowadays, that's all in the trash can, much like your large television sets have gone to the trash can. Nowadays, it's all about lasers and photo sources. So strain gallium arsenide with laser on it, photoelectric effect liberates the electron, accelerate, bend, so low energy being bent up to the top, come around, accelerate again, and go around as many as 5 times in the original design. I have 3 end stations. I can pick off whichever energy you like. So originally this was a 4 GeV machine, upgraded to a 6 GeV machine. Down in the tunnel, there was space at the end of each of those linacs to add more modules. It actually goes absolutely beautifully that we can upgrade this machine yet again to 12 GeV in the space provided, because digging has gotten prohibitively expensive. So this is a photograph of what the site looked like from above in the early days. And you can already see the outline of what's coming, the injector, the accelerator. And when you have an empty site like this, you can do things in a way that's much, much easier than if you already have a site. I mean, they're trenching the entire facility to get this built. That's kind of easy. When we want to do upgrades, like we talk about a positron source, we're now talking about locating that behind this injector. We'd have to dig right behind there, almost straight down, because I've got buildings located all around. A little bit later picture. This is the Canon plant behind us. Coming together. The tops of the experimental halls, similar technology to building oil containers. And you're seeing the service buildings that power our accelerator. So underground, roughly 30 feet down, is where the superconducting RF cavities are that Ryan talked about. Above ground's where we keep the electronics, keep it out of the radiation environment as much as possible. It's also very practical. If a lot of things can be fixed upstairs, I don't have to access the accelerator. I can just go into a service building and get it fixed. Experimental halls coming along. So some photographs. This is one generation of our source. So inside this fancy aluminum container is strained gallium arsenide. It looks like a little black wafer, but it looks like nothing. But it is really at the heart of what Jefferson Lab does nowadays. Very special material, very hard to procure. The strain allows us to have 85% electron polarization. So electrons spin one half particle, right? So I can spin either way. If I use a bulk gallium arsenide polarized laser light, I'll get about 35% polarization. That was considered great in the early days of doing polarization experiments. By adding the strain, get up to almost perfect polarization. And if you're thinking, why the heck does polarization matter? I'll suggest you've done experiments. So if you've taken a bar magnet and another bar magnet, and you bring them together and they start pushing apart, then I repeat that experiment, flipping the bar magnet, they click together. That's very similar to what's happening when I take this electron beam and have it polarized one way with a target. And I polarize the electron beam the other way and hit that same target. It allows us to learn more information about what's going on inside the nucleus than just scattering. I'm making use of a new degree of freedom. And this has been huge at this laboratory and is a lot of our scientific program. So one of the big experiments coming up is molar, this parity violation experiment. You can't do that experiment without having a highly polarized beam. Even with our 85% polarization, it's going to take 3 years. And this goes as p squared. Right? So if I'm back down to the bulk MR science, more than a decade. So a lot of these, Ryan showed you some nice pictures, nice clean accelerator tunnel. When did it ever look like that? Anyway. And also that arc. Again, it's worth pointing out. So that beam, when it comes to the spreader, it's just a dipole magnet. It's like a prism. Electron comes in. If it has low energy, it's bent a lot. If it has high energy, it's barely bent at all. Just like colors of white light going through the prism get spread out by their energy. The beam gets spread by a dipole magnet by energy. The lowest energy at the top and the magnets at the top are small and they are spaced well apart. And as you get down to the higher energies, the magnets are getting bigger and bigger and bigger. And these are the newest, baddest 12 GeV magnets that bend the beam around. All right. Skipping ahead. So in the early days of Jefferson Lab, we have 3 experimental halls, each with a different main focus. This is experimental hall A. You're going to go in this hall. It doesn't look anything like this anymore. If you look carefully, you'll still see the spectrometers. One of them is now used to hold up an air conditioner. This depresses me, but it's factual. This is the way the hall looked like when I first got here as a student. The electron beam is coming in from this side, a lot of diagnostic equipment along the beam line, multiple polarimeters, molar polarimeter. We also had a Compton backscattering polarimeter, and in the very center of the hall, a target. And this could be as simple as a foil of carbon. You want to do a carbon knockout experiment, so-called E'P experiment. It could be liquid hydrogen, deuterium. We've run polarized helium-3. We've run tritium in this hall. Tritium is cool. It's radioactive. It causes a lot of excitement. We can run lead. So pretty much the periodic table, if I can make it into a target, we can run it. We can run gas targets as well. The tritium was a gas target. We've run argon. So the material you want to study. And then we had 2 spectrometers to detect the particles knocked out. We could set which polarity you'd like that, whether you want an electron and proton, both electrons. And in this hall, we really can let it rock to the highest beam currents that CEBAF can deliver. And we can handle up to a megawatt of power going through this hall. Next hall, experimental hall B. This one's more like your hollowed out egg. Put a target in the middle and detect everything coming out. So multi-particle final states are what's best in this hall. It's actually relatively low current or low luminosity. So if you look at this 10 to the 35, 10 to the 38 per centimeter squared per second. The important bit here is I'm going down several orders of magnitude in current, in luminosity when I go between those 2 halls. But the data rate is the same. I'm often limited by current technology and all the halls. CERN in Switzerland, we're all limited by how much data I can push onto a tape and record it. I can do all kinds of tricks. I can try to pre-process, but in the end, I'm going to be limited by how much data I can put to tapes. I can throw money at that problem, but you get stuck pretty fast. So even though the halls take very different currents, the amount of data they put on tape is about the same. But one sees everything. The other one can see at a rate 1,000 times higher, but now they look at things very precisely. The concept there was one hall can see the big picture. If you see a bump, a wiggle, you think you see a new particle, you then go to hall A, set the spectrometers, and find out real quick, was it real or was it a pentaquark, which wasn't real. All right. And experimental hall C, also a 2 spectrometer hall. Back in the early days of Jefferson Lab, this was a hall we would configure for major new setups. That has changed. This hall is now always the 2 spectrometer hall, or almost always. And hall A is where we do major new setups. And you're going to go down on Friday and see one of those setups. So this is the image of the upgrade. So we started out with this machine, 4 GV. They were able to get 6 GV, little upgrades. We had a big upgrade, adding more cavities in North Linac, South Linac, able to get 11 GeV to our classic end stations at this point, ABC. There were some detector upgrades, but the big addition was adding experimental hall D, which is a real photon hall. So they take this beautiful electron beam, and the first thing they do with it is smash it into a diamond and make polarized photons. The electron beam is then dumped, and hall D uses only photons. There's no electron hall. But this really added a new capability to Jefferson Lab. That's not something the other halls did. So nice complementarity, adding another hall, looking for exotic particles made from photoproduction. This is what that hall looks like. All right, so this is aerial photo. This is after the 12 GV upgrade, but it is from a few years back. This is when there were still buses parked here. So I think it's about 7, 8 years ago. It's amazing how fast corporate world changes. This is all gone. We now have new buildings through here. Nevertheless, a lot has stayed the same over the years, where the injector is, where these service buildings are, the domes of the halls. After the 12 GV upgrade, adding a Tiger vault and experimental hall D. Hall D is above ground mostly, whereas the other 3 are deeply underground. And we are here. All right. So for each of those experimental halls, it's really an army of people that makes it possible to do the experiments. So if you have some great idea for an experiment here at Jefferson Lab, we have a program advisory committee. You come into that committee, roughly 1/3 make it back out with improved experiment. So it can be pretty rough. Nevertheless, at a user facility as a Department of Energy, you do not pay to do an experiment. We will do the experiment, but still, it needs to be world-class and make it through an advisory committee. Once it's through that committee, the laboratory will put a lot of resources into making it happen. That's often making the targets. And on this slide, these are the targets that are running right now in 3 of the 4 experimental halls. So one hall is under construction. That's one you're going to see on Friday. The other 3 are running beam. One of them has a hydrogen gas target. One of them is running with cryogenics, liquid hydrogen, liquid deuterium, and another cryo target, much smaller, also able to run liquid hydrogen, liquid deuterium in hall D. This is just one of our support groups, roughly 10 people, takes care of making all those targets, servicing them, getting into the halls. It's not just the targets, it's also the electronics, the technical staff to make the superconducting magnets work. Even something as simple as rotating the spectrometers, the bogies, making sure they work. It's really an army to make the halls work. Then add to that, I also need the accelerator to be working at the same time. Really bringing that all together. A lot of people make the science, but it's also about our user community and those world-class experiments that come. So in July, if you're here, right after 4th of July, there'll be a program advisory committee meeting in the auditorium, and you can watch them give people grief about their proposals. Some of them will be world-class, some of them will, it can be rough. I can assure you, none of those proposals is bad per se. They're all written by really smart people. It's just that you're going to get into a room with a lot of other really smart people, and they're judging you relative. What is the best science? What are we going to devote our resources here at the lab? At our program advisory committee, we have broken the science that we do here into 6 categories. nucleon structure, form factors, parton distributions, excited states, resonances. This would be as simple as pion production, the delta resonance. 3D imaging of quarks, so generalized parton distributions, deeply virtual Compton scattering. One of my favorites, short-range nuclear forces, short-range correlations in the nucleus. Searches for exotic matter, that be a glue ball. It's one of the things experimental Hall D has been searching for. And then finally, like the Molar experiment, tests the standard model, really looking for physics beyond the standard model. One thing I find amazing about Jefferson Lab, even though we're a small part of the budget for nuclear physics, 1/3 of all people in the United States with a degree, PhD in nuclear physics, came through this facility. And since 1997, I mean, this graph is almost perfectly linear. So hundreds of PhD students have come through this laboratory and basically in equilibrium with 200 PhDs in progress at any given time. So just to touch on the science, just a couple topics. You're going to hear all kinds of topics over the next couple weeks of things we do here at the lab. These are just a couple of the experiments I find personally fascinating. Proton radius experiment. So a few years back, everyone would have told you the proton radius is 0.88 femtometers. And if you said anything else, you would get yelled at. I know because I said something else. So I had a summer student, unlike yourself. We analyzed all data and we got a different number. We got 0.84 femtometers. There was an atomic experiment that came up with a very precise result where instead of using electrons to determine the Rydberg constant, the ionization energy, they used a muon. They were looking at certain transitions. Their extracted radius was much smaller than this 0.88. They actually got to 0.84. Caused a lot of controversy. Is that physics beyond the standard model? Something special about muon instead of electron? A lot of data. We're taking another experiment right now called PRAD2 with electron scattering. Understand what's going on. At the moment, it really looks like there were some problems in the original extraction, and the proton radius actually is 0.84. This is going on right now. Another one of those experiments where everybody knows the answer ahead of time. Proton form factors. So you pull out old textbooks. What's the ratio of the electric to magnetic form factor? It should be 1. If you take any really naive model of, okay, I've got a proton, I'm gonna make it up of some up and down quarks. So those quarks have charge, magnetism. The ratio of that should be 1. Why should it be anything else? Proposal came into Jefferson Lab. They actually wanted to do physics beyond studying the proton, but a proposal was put in to do the proton form factor ratio, which we all knew was 1. Okay, yes, you should do that experiment. We already know the answer. They got a very low scientific grade. We went to do the experiment, and if you've looked at this plot for more than 1 second, the ratio of the electric to magnetic form factor of the proton as a function of form momentum, this is the kick given to the system, it's not 1, it's not even close to 1. It changes dramatically. So these different points with different symbols, those are different experiments we've done over the years. The most cited result from Jefferson Lab is Mark Jones's paper. He's now the Hall leader over at Hall AC. Was the form factor ratio and this deviation from unity. No one expected it. And this is where science always gets exciting. When you go to do the measurement and it's not coming out like everyone told you it would, you first assume you did something wrong. You check, double check, triple check, everything looks good, publish it. Oh, still, something's probably not right. Redo the experiment. Other people have done the experiment. No, the form factor ratio, this was done with polarization observables, changes dramatically as a function of Q squared, unlike previous expectations. Another fun one, and this gets to one of my favorite topics, short-range correlations. proton, neutron, nucleus overlapping strongly. By taking inclusive scattering data, just electron in, electron out, taking ratios of heavy nucleus to deuterium. You take that data, plot it, you'll get these plateaus. This is data from Donald A. It's actually from Slack. You do the exact same experiment, but in very different kinematics, deep and elastic scattering kinematics, you'll get this downward slope. This is known as the EMC effect. Deep and elastic scattering, EMC effect, something changing with parton distributions in the nucleus. Short range correlations, proton, neutron coming together. This paper and this paper were published and had nothing to do with each other. What I find fascinating, this data is all from the same lab. It's all from Slack. It was from the same hall, and nobody noticed that the magnitude of this slope and the magnitude of this plateau were exactly correlated. We've now done a lot of experiments and shown this correlation between this EMC effect, the deep and elastic scattering effect, which couldn't possibly have anything to do with nucleons and nucleus coming together, seems to actually have a lot to do with nucleons and nucleus coming together. So again, one of these experiments where you actually could have seen it ahead of time. This data was actually all available for 30 years. We're going back, doing experiments, notice the correlation, and then it's all of a sudden like, oh, wow, this is actually staring you in the face in the literature. This connection between short-range correlations, nucleons coming together, and deep and elastic scattering effect. The reason no one saw it is they had it in their heads that there was no way they could be connected. It was a preconceived notion. And those kind of biases kill us, not only in, let's say, everyday world, but as scientists, you have to watch out. That preconceived notion, and you won't even realize you're doing it, will cause you to miss something. And the person who actually sees it also, wow, you got it. And this is that. So taking the data and just plotting the magnitude of the plateau versus the slope, short range correlations, EMC effect, see the linear. This is now an old plot. There are a ton of data points now put on here, making this connection between two effects that people originally thought couldn't possibly be connected, though my graphic artist could easily connect them by showing, oh, yeah, the partons and nucleus could be distorted if they're coming close together. Okay. So last year, this facility did absolutely amazing. We had one of the best runs we've ever had. The accelerator was up 85% of the time, running 1,060 MeV per linac. Beam power is almost up to 1 megawatt. Low trips, great machine. And I could stand up here and hand wave that. This is a nice letter written by our user board of directors noting how well we ran. It was unusual though. That's actually part of our problem. This machine has been upgraded for it's over 10 years now. That was the first time we ran at 85% efficiency. We have struggled with a lot of the new modules we built. They are not as stable as the original. So back to Ryan's talk, lots of different cavities, C25, C50, C100s. That's the amount of gradient you get per module. Some of these C25s just run. They were built on day one. They'll probably work till the end unless we pull them out. They just go. They're unstoppable. These brand new C100s, a truck drives by, they trip off. I am not exaggerating. When the nitrogen delivery truck drives by, driving too fast, it trips off a C100. That's how sensitive they are. It's been problematic. We put a lot of effort into understanding why they trip off. We developed something called a C75, little less gradient, a lot more stable, a lot better performer. But we've gotten there. We've gotten to the point where we can run this machine very reliably, and we're looking to maintain that going forward. So right now, we're doing a run where we're really showing off the dynamic range of this facility. We've dropped the energy down to 345 MeV per linac. This is to go after mostly a proton radius where they'd like to get to very low for momentum transfer, so low energy, fantastic. Also doing some sort of classic nuclear experiments, mostly checking results from Mainz, our sister lab in Germany. And in Hall D, they're running their first low energy run. Starting on Monday, next week, there'll be a 2-week down period. We're going to rescale this machine back up to its standard energy. At that point, Hall B will be taking first pass. They're going to be doing their middle Q-squared point. Hall C is going to be doing deep elastic scattering, cryotary experiments. And Hall D is back to full energy, and they're going to complete what's known as GLUX2. This is the second of their big experiments looking at photoproduction. And if I lay that out in experiments by numbers, these are just the spokespersons of all these different experiments. You can see the different universities involved. It's really amazing. This is just one experimental period, lots of different people involved, lots of different experiments, a lot of different science being done at the lab. And while we're doing all this in parallel, we're also working on something called Molar. And Molar is really the flagship of the next 5 years at this laboratory. So right now we are building it. It's the biggest construction we've done since the 12 GeV upgrade. So brand new spectrometer going into Hall A. It's going to do parity violation experiments. Going to run for about 3 years. During that time, that's really going to take a lot of our resources. It takes a lot of our beam power. And this is where it gets interesting. So yes, Jefferson Lab has multiple halls. We can do a lot of different science, but it's not an unlimited resource. This machine can only run roughly a megawatt of power. And Molar wants nearly the full megawatt, and they want the full polarization. Basically, they want it all. So the fun part is figuring out, okay, what else can we do during that time? By setting the beam energy very precisely. Even though Hall A gets full longitudinal polarization, that doesn't mean the other halls can't have polarization. I just have to think a little. So spin precession, G-2, the anomalous magnetic moment of the electron. So for given energy, I can calculate where the spin precession will go to the various halls. By picking what I call magic energies, I can actually line it up so multiple halls get either full polarization or close to it. So we will be able to run polarized experiments Hall B. Hall B also runs very low current. No problem. Hall B and Molar are compatible. Hall C, typically we run high current experiments in Hall C. That wouldn't work. At least not at the highest energy. It's really limited by power. So moderate currents going down to the lower passes. What can I do? There's an A-rated hypernuclear experiment. This will be another big installation, special magnets down the hall, but it's compatible with the Molar run. Hall D, low current again, easily compatible with Molar. So in thinking about scheduling, doing different experiments, the way I do it is almost as I just described to you. There'll be a flagship for the next 5 years, that's Molar, and I'll build a picture around it. And visually, this is what that looks like. There's a lot of information on here. I just want to look at these hashed areas. That's when we're doing a big installation in one of the halls. Molar. When Molar finishes installation, next big installation, hypernuclear. So the resources, the technicians, designers, engineers switching from Molar to hypernuclear. And if I go further out in time, K-long, a new experiment for Hall D with kaons instead of photons. So it's basically one giant installation at a time going forward, and then figuring out experiments that can run with each other that are compatible. And this plan will change. So we typically make a plan that goes out 5 years. We review it once a year, always marching out in time, trying to optimize the science. We take the recommendations from our program advisory committee. If there's a really hot experiment, wow, someone's seen a new particle, they have evidence of dark matter, Jefferson Lab, check that. That'd be something we'd move to the top of the list very fast. But we really take that advice from our program advisory committee. What is the most compelling science and it gets reviewed. If you put in an experiment, we have something called Jeopardy, where it will get reviewed. So if it hasn't run, and we have quite a backlog of experiments, if you haven't run after 3-4 years, it'll come back to Program Advisory Committee. They'll review it and they'll say, yes, your science is great. They sometimes even say it's gotten more important to do that experiment. And other times they go, that's no longer that interesting. We already know that's rolled out from another lab or another experiment. But it keeps the science fresh. It can sometimes be challenging. Nevertheless, when you're making use of federal resources, we really have to be doing the best science that we can. So that brings me to Mueller. This is the hall you will be going in. These are what are now my old spectrometers, one of them holding an air conditioner, and the new Mueller spectrometer. It has been quite a change. This is a picture of Hall A in September 2025, set up for a completely different experiment. This is super big bite. This big detector on the floor, plates on the floor, so you could change the angle by dragging this thing around. We had to remove all of that and begin installation of this Mueller setup. So we went from this mess to clean hall. This is early this calendar year, and then bringing in the equipment for Mueller, power supplies, shielding blocks, and they're just now starting to build out the spectrometer. So when you go down there, you'll see more of these pieces have now been installed, the so-called pion donut mounted to the beam dump, and this whole area is going to be filled with detector. This is roughly a $50 million project. It should complete roughly this time next year, a little sooner, hopefully. To wrap things up, I will say, if you talk to people, not just here at Jefferson Lab, but in nuclear physics, this has been a rough year. There's a lot going on, and I've been here long enough. I've seen the years where we've had the bad budgets. I've been here when we've had the great budgets. This year, there was the government shutdown. My sister-in-law works at the Coast Guard Academy. She was deemed a critical employee, so she had to work, but she didn't get paid. At Jefferson Lab, we're an M&O contractor, we were allowed to keep going on the funds that we had in the bank. So we had roughly, with a lot of effort, we were able to keep going 6-7 weeks. Basically, the same time the government shutdown ended was when we were running out of money. We were making all kinds of plans for how we were going to shut this machine down safely. You go, oh, just turn it off. Well, we have a lot of liquid helium on site. And without the power on and continuing to pump on it, it's just gone. We do not have enough storage capacity, nowhere near the storage capacity to hold on to our helium if you let it warm up. It's basically irreplaceable at this point. So you can imagine we're freaking out, trying to figure out how long we could keep enough power on to keep our helium. We had to plan for that this year. That was the government shutdown. January, we had a workforce reduction. So right now in the budget cycle, we're on the downslope. We did have to reduce our workforce. Never fun at any employer. And right now we are near the end, but still within this M&O contractor transition. We're going to have a new organizational structure at the laboratory. So at the beginning of the talk, I mentioned that my title is changing. Part of this reorg, we have a new org chart. You take over a new company, first thing you have to do is reorganize it, right? That's coming. Other things that are happening this year. Genesis, American Science Cloud. This is an initiative within the Department of Energy to make use of AI. The current administration really sees this something like a Manhattan Project. They have all 17 labs working towards AI, machine learning. It is part of our future. It's actually already part of our funding profile now at the lab to work on these endeavors. A lot of it's still basic research, but now it's how do we make use of these new tools? How can I use it to analyze data better, faster, new tracking algorithms, faster extraction of the observables we want to get from our scattering data. And we're very much focused on delivering for the Department of Energy what they call 413.3 projects. It is as horrible as it sounds. One of those is Mueller. It is an official project of the Department of Energy to deliver a major piece of equipment that is Mueller spectrometer. The other thing we're doing here at Jefferson Lab is we are working on 25% of the Electron ion collider scope. It is coming through this laboratory, which is huge for us. It's a several billion-dollar project, and 25% of that will flow through Jefferson Lab. And at a very high level, the goal for our new lab director is to change this laboratory from being single purpose, single mission, becoming that multi-program, multi-mission laboratory. And I'm going to end today on one of the ideas for that future. It's one I like a lot, which is adding the ability to run positrons at Jefferson Lab. Conceptually simple. I have an accelerator. If I flip the polarity of all the dipole magnets, I can run positrons instead of electrons. I just need a source of them. Though since I'm a physicist, I don't just want positrons. I want polarized positrons. And it turns out that if you start with polarized electrons and do pair production, you'll actually create a polarized positron. We've done that, it's published in PRL. Now the trick is to scale up from a little demo experiment to something that would work in this main machine. There are different ideas afoot. The original idea is we take something called the LERF. This used to be a free electron laser. Build the positron source, dig a tunnel, feed that into the main machine, get that accelerated, and I'd be able to do positron experiments with Jefferson Lab. There are now ideas about actually turning what is currently called the LERF back into a free electron laser for basic energy research and building the positron source this location. From a science point of view, I don't care. I would just like to have a positron source that could feed CEBAF. There are already a number of experiments. These have been reviewed by our program advisory committee, and this gets to the typical chicken and egg problem. Do you allow this program advisory committee to review these new experiments before you've actually gotten a critical decision 0 from the Department of Energy to go forward with the project? It can be tough deciding how you're going to do this. And what the heck is a critical decision 0? Sounds horrible. So projects, Department of Energy loves projects and project management. And the very first step in a project, these typically are things that cost 50 million. I think they've raised the limit now to about $100 million or more. They're going to be managed. How that money's spent is going to be carefully tracked. And they're gates. And the very first gate is the Department of Energy making a statement of need. That is critical decision 0. So all these projects have gotten a critical decision 0, statement of need. You then work through different levels. You're really spending money building things when you get to critical decision 3, and critical decision 4 is you've built it, you are good to go. It is a technique to ensure that the money is managed well and we don't have the fiasco we had with the superconducting super collider. There were other reasons as well. That's one example of a big Department of Energy project that was not managed the way they do now, that did not succeed, and I believe they use it for growing mushrooms. This was a big collider we were going to build in Texas that did not come to fruition. Anyway, with positrons, lots of science has been reviewed by our program advisory committee, just different aspects of science, whether it's understanding two-photon effects, understanding why that proton form factor deviated from expectations, 3D imaging, or searches beyond the standard model. All can be done with positrons. They've all been given a scientific rating, and they've all been given a condition, the condition being actually build positrons. So this is one of the 17 national labs in the Department of Energy System. We can run multiple halls, a lot of different science topics within field of nuclear physics done here. Occasionally, the experiments we're doing branch and kind of cross this almost imaginary line between nuclear physics and high energy physics. For those who care, the X17 experiment, looking for a dark matter candidate particle, that's actually considered a high energy physics experiment. Nevertheless, this is a nuclear physics lab. The bulk of what we do is by definition nuclear physics. It will do a lot of different experiments, 4 different halls to do it in with the CEBAF accelerator, able to do many different beam energies. We can scale the entire machine up, down, get different degrees of polarization, not only in plane, some of the experiments want normal polarization. We can do it all. We are in the midst of a lot of change at the labs, so it's kind of a neat time to see that transition between 2 different agent or companies running the lab. A new organizational structure coming. And it will be fun to see over the next decade, Jefferson Lab transition from this single purpose lab just doing nuclear physics to something doing nuclear physics, high performance data center. Maybe this new FEL will come online, terahertz radiation, basic energy science. They even want to do things that are classified. It's something we've never done at this laboratory or done very little of. And that is what I have.